Hello class, this is Ms. Riggins with today's video on section 9.1 Identities, Expressions, and Equations. After watching the video, please remember to write down important notes, equations, statements, formulas, and identities, and feel free to pause, rewind, or replay the video as often as you need so you can get a clear understanding of what's occurring. When you have concluded watching the video, write a brief summary of what occurred in the video in your notes and submit that summary as well as a top question via the online whiz form the day before class. All right, let's begin. You are going to need notes because we are going to write down some very important formulas and equations that you're going to be responsible for memorizing and knowing, especially for the final exam, but also in life as well, too. Okay, so the topic is identities, expressions, and equations. And a question that may come up is, what is an identity? And the thing about identities is they look very similar to equations. And so I'm going to give you two examples, one of an equation and an identity, but why they're different. So in this case, we have here an equation, 2 times x minus 1 is equal to x, and an identity as 2 times x minus 1 is equal to 2x minus 2. Well, I know some of you are saying, well, what's the difference between the two? Well, if you notice, for the equation, you will only have one solution, and for the identity, it will be infinite solutions, any value of x that works. That's what makes the difference between an equation, i.e. that only has 1 or 2 or 3 or a finite number of solutions, and an identity which has infinite solutions because every single value of that the variable can have will work. Okay, and in trigonometry we have a lot of identities because the function is periodic. Trigonometric functions are periodic. One such identity is Pythagorean identity. It doesn't matter what angle theta is, but regardless of what it is, cosine squared of theta plus sine squared of theta will always equal 1. And we can also look at a relative of the Pythagorean identity by dividing everything or both sides by cosine squared theta. And then we end up with 1 plus sine theta over cosine squared equals 1 over cosine squared. And it gives us another identity based off Pythagorean theorem, which is 1 plus tangent squared theta is equal to secant squared theta. That's an identity you need to memorize. If it's in a blue box, you need to memorize that. Okay? And even if you can't memorize it, if you start off with the Pythagorean identity and divide both sides by cosine squared, you'll get the same resulting situation. Okay? All right, and this works for whatever theta that you have. Now, there are plenty of different identities. Some I don't expect you to memorize, but some you will have to memorize. And we'll be going over a lot of them in this video, as well as examples, because I hear you guys like examples. But the question may come up is, why are we using identities? Why are they helpful? And several reasons. Number one, identities help us to simplify expressions. Here's an example. And if someone says, just graph that, you'll be like, oh, that's a lot of different things to graph. But if we can use an identity to simplify this, then we might not have to have a difficult time with graphing it. Well, what identity can we use? Well, we can use the fact that sine is an odd function. And then we can use the fact that cosine is basically a pi over 2 shift of sine in a certain direction. And so what I'm going to do is I'm going to replace this with the identities that we do know. And because it doesn't matter what t is, as long as t is in the domain of sine, we'll be able to answer this question. So in this case, we're going to use this to replace this with this. And we're going to use this identity to replace this with this. I'm sorry, that's the same thing. With this and with this. Okay, got ahead of myself. Okay, so as a result now, when I do that, I have simplified this statement into nothing but in terms of sine, which I like because then I can combine these signs into one sine expression. And the graph of 9 sine t is so much easier to graph than the graph of 2 sine t minus 3 sine of negative t plus 4 cosine pi over 2 minus t. Okay? So again, identities are helpful in helping us simplify expressions. They're also helpful in helping us evaluate expressions. So suppose they say cosine of theta is 2 over 3, and they want us to find sine theta and tangent theta, where theta is in between 3 pi over 2 and 2 pi, which we all know is the fourth quadrant. So if you didn't know, fourth quadrant. Okay, so how do we go about using identities to help us? Well, I know that cosine squared plus sine squared is equal to 1 from the Pythagorean identity. So since cosine of theta is given to be 2/3, then I can replace in the Pythagorean identity with what's given and end up with something that looks like this. And then to figure out what sine is, I get sine by itself. And I have an answer. That sine theta is equal to plus or minus square root of 5/3, okay? But since we are in the fourth quadrant, if you recall, that means sine is always going to be negative in the fourth quadrant. So therefore, our only answer that we can get is negative square root of 5/3. We can also use a trigonometric identity to figure out what tangent theta is. And tangent theta is sine theta over cosine theta, that identity we know. So now that I know what sine theta is, and I already was given cosine of theta, I can just do the simplify this fraction and get my answer for tangent theta without having to use a calculator. Fancy that. We can also use identities to solve equations as well. So here I have this equation, 3 sine of theta is equal to square root of 3 cosine of theta for theta between 0 and 2 pi. Which theta values work? Well, I can divide both sides by cosine of theta. And so that kind of leaves me with 3 times sine theta over cosine theta is equal to the square root of 3. And then I know that sine theta over cosine theta is tangent theta. And then I can get tangent theta by itself by dividing by 3. And I get that tangent of theta is equal to 1 over the square root of 3. I know some of you are saying, okay, well, that's good, but how do I get what theta is? That's why this finals project of memorizing the unit circle will help. Well, actually, the final project isn't to memorize the unit circle, but you will need to memorize that project that you did to help you answer these questions that are going to be on your final exam. So here we have, now that I didn't try to figure out what theta needs to be, and some of you will go to your calculator, but you won't always be able to use your calculator to do, arctangent. So you're actually going to have to rely on the fact that you memorize the unit circle and you know that pi over 6 will give you a tangent ratio of 1 over square root of 3. Because sine theta over cosine theta will give you that ratio, okay? And therefore my answer is pi over 6, and I check to make sure it's in the domain. It is, and I'm done, okay? You can also say, wait, you're not done because tangent is also positive in the third quadrant, and this goes through the third quadrant. So I have to add pi to that to get 7 pi over 6. So those are my 2 solutions. Okay? All right, moving on to the last thing. I think it's the last thing. Oh, the double angle formulas. This is the most important thing because you have a lot of different identities that you've never seen before. I'm going to explain why it works, and then you're going to memorize. That's how it works. So let's take a look at sine 2 theta and 2 sine theta. They both involve sine, but they have different amplitudes and different periods. Do we have an identity that involves sine of 2 theta? Well, let's actually look at a triangle that has an angle of 2 theta. And as you can see here, we're 2 right triangles put together. So now we have an isosceles triangle. And this angle is actually 2 theta. Okay. And we're going to solve this. How are we going to solve this? Well, first, I'm going to use law of sines to say sine of 2 theta is across from the side. That is 2 sine theta. Oops, sorry. So that's what this is. And the sine of alpha is across from the side that is 1. So this is the law of sines, because this is not a right triangle. This is a isosceles triangle. And so now if I can somehow represent sine theta in terms, sine of alpha in terms of something that I can use, I can, because, draw a string back. Let me move this up here so you can see what I'll do here. Sine of alpha is equal to the cosine of theta, okay? Why do we know that? And this is time we're taking a look at this triangle. Okay, and we talked about that before, but simply opposite over hypotenuse, that's the same thing as the adjacent side to the theta angle, which is cosine theta over 1. So that means I can replace in this problem sine of alpha with cosine of theta. And when I do that, I end up with this ratio because of me replacing sine of alpha with what cosine of theta. And then I can just solve for sine of 2 theta by multiplying both sides, and now I have a double angle formula for sine as well. And that sine of 2 theta is equal to 2 sine times cosine theta. All right? So find all the solutions on the equation for which they're equal. I can solve this graphically by just graphing the two equations and trying to identify where they're equal. And as you can see here, they're equal 3 places. They're equal at t equals 0, t equals pi, and t equals 2 pi on this interval. But I can also solve this algebraically using the double angle. So as you can see, 2 sine of 2t by the double angle formula is 2 sine t cosine t, which is equal to 2 sine t. I can subtract 2 sine t from both sides, factor out a 2 sine t, and I get 2 sine t times cosine t minus 1 is equal to 0. So in other words, 2 sine t equals 0 or cosine t is equal to 1. And so the only place where sine is equal to 0 is at 0 and 2 pi. And the only place where cosine of t is equal to 1 is at pi. Okay, so either which way we can use the answer to get our solution. A couple more double angles, but instead of for sine, but for cosine. We're using the same exact triangle, isosceles triangle, but this time we are going to use law of cosines. And if I want to find the cosine of this particular angle, I could use the law of cosines. That's my washing machine being loud. So if I'm trying to find the cosine of 2 theta using the law of cosines, it's the side across, which is 2 sine theta squared, and then I square that is equal to the other side squared, this and this, minus 2 times the product of the two sides times the cosine of 2 theta. So trying to simplify and get cosine 2 theta by itself, I get 4 sine squared is equal to 2 minus 2 cosine 2 theta. And so therefore, getting cosine 2 theta by itself is equal to 1 minus 2 sine squared theta. I would do the more algebra. We don't have time. It's already 12, almost 13 minutes. Okay? So I also can solve for cosine theta using the relationship between Pythagorean identity. And this is another version of cosine 2 theta, because since sine squared plus cosine squared is equal to 1, Pythagorean identity, sine squared is equal to 1 minus cosine squared theta, and that's where I have this, and then also I have this as well. And you can do that algebraically using the Pythagorean identity. And then the double angle for tangent, we're not going to have time to prove it, but this is that double angle for tangent, so make sure you know these as well. Okay? And I think that's it. Yeah, that's it.